Hi, I'm Pakata12 and today we play with my favorite operator in experimental TouchDesigner, and that is neighbor pop. And this little thing here, it's extremely powerful, and we'll use it to solve collisions. And this is my second tutorial in pops. The first one I released 2 days ago, and you notice I took my cap off in amazement for pops. So yeah, we build this network. Everything it's textures, let's say, and we use the neighbor pop to solve collision. And I also have a network very similar in which everything is pops, and of course the collisions done in textures. And yeah, those two would be available for my patrons in tier 2 play. And I also have something much more advanced for my patrons in tier 3 learn, in which we work with the fit to square texture, which it's the most optimized way of working in textures. And yeah, so today we build this from scratch. And yeah, I'll have it aside to guide me. And yeah, let's start clean. Okay, so we need a constant chop, and let's set the particles. Let's go with 12 for now. Radius, it's 1 divided by 6. Okay, and now we chain a null here, and we call it data. Okay, now I would like the starting position for my spheres to be in a circle. So let's build a circle. We use a ramp, okay, and let's drag the particles amount. For the resolution X, we go inline texture. Okay. Okay, and now let's have a null here. We insert a null in between, collapse selected, and we have a folder. Let's name this folder radial. Okay, and here inside, let's use a math. We want to multiply this ramp with 2pi. So 2 multiply with math.pi. Okay, and now we use a function. Okay, and let's set this function to RGBA. For the red we go with the cosine, for the green we go with the sine, for the blue we go with a constant 0, and everything is radians. Okay, and let me check. Yeah, this ramp has to be 32 mono. Okay, now we are good. Let me put everything nearest pixel. Okay, and yeah, let's use some spheres to instance to see what we're doing here. So I will name this position. Okay, and I'll give it a pink color, and let's have a noise for the radiuses. So we drag the particles again to have this the same resolution. This is 32 mono, and the noise is offset 1 and amplitude 2/3. Okay, and yeah, now my values is not actually the radius, is the scale. Okay, so the radius is 1 divided by 6, and then we have we want some variation, and yeah, with this scale we have it. Let's use a limit. Now the values here are in between 1 minus 2/3 and 1 plus 2/3, but sometimes it goes above and under, and I would like to limit here with clamp the scale to 1 divided by 6. That doesn't have any relation with the radius yet. It's just minimum scale, okay? And here we go with 2. Okay, and now we have a null. So let me check, we clamp it, okay, and this is scale. Okay. Now let's have a sphere. We can choose either sphere pop or sphere sop, doesn't really matter. And we go with a polygon. I choose a sop, frequency 4, and let's drag the radius. Okay, and now we use a geometry. Okay, and we drag the position and the scale. And we go here with R, and here RGB. Okay, now let's see. So we don't have any sphere touching. Okay, but I would like to move this circle from the center 0 to move it in between 0, 1. It will be much easier for us to see the colors. Okay, so I will use a matte, and yeah, we can offset this with 1 divided by 2, but the radius is too big, so I can multiply this with 1 divided by 3, so I will have a smaller circle. Okay, and yeah, they are now in the same plane, and I would like to solve this. Let me mask the alpha. Okay, and this is nearest pixel. And now if I have a noise here, I can change the position a little bit, and so they will let's go with 0.1. Okay, okay, and yeah, we good. Now they are not in the same plane. Okay, now let's have a feedback here. Okay, I'll have this black. Let's have this smaller a little bit and have it here. And also a keyboard in chop to pulse the feedback. Okay, and now we drag this position into our feedback. So in this loop here, we have to solve the collision. And let's go with the top 2 pop. And we have the points. Let me put everything nearest pixel once again. Okay, and we have this top 2 pop, and we go with position RGB. Now we have our points here. Okay, and now my favorite operator, neighbors. And in the neighbors, I have to set the distance to check for the neighbors, okay? And that would be the 2 times my biggest radius. And the biggest radius is my scale, which it's 2 here. Let's drag this 2. Okay. And yeah, my radius, I will drag it here in the max neighbors just to have it for the copy. Okay, and we multiply here like this, and then I multiply with 2. Okay, so this is my search distance. In a distribution, we go with the closest. 5 neighbors, it's good for now. And here we want to output the neighbors. We don't need num neighbors. That is super easy to find. Okay, we have everything we want. Now, I saw several tutorials in POPs, and they were saying it's impossible to make use of the data inside this operator without GLSL. And that is not true, obviously. So we go with pop to chops, and you will say, hey, but those are not as fast. And it's also not true. Okay, let's go with neighbors. Okay, now years ago I saw Vincent Hoos transferring 100,000 samples into chops, and then went back into GLSL and so on, and that should be the weakest point, but it was not. So I'm imagining for some amount of points you are good with this, and yeah, that amount is tens of thousands of particles, so we are good. Now we have those neighbors, and because I love tops, let's go into tops. Okay, and we have this this little texture, and it seems a little bit confusing. It's black and white. Let's take a look in this neighbor pop. Take a look with a pop to dot. Okay, now we have the position for each of the spheres and the neighbors. Okay, now let's go with a little bit smaller radius, maybe 1 divided by 12, let's say. Okay, now only couple of them are touching. Okay, now let's see here what this means. So you see here are quite a big number, like 4 billion and 294 million and so on. And this is huge. Okay, and what that means is where we have this huge number, we don't have any neighbor. Okay, and yeah, don't worry, we don't have to delete, search for those huge numbers and delete them. Okay. Okay, now my white texture, it's having those 5 columns of neighbors, and some of the pixels are having that huge, you see here, it's a huge value. Okay, now out of here I will have a null, insert a null in between, and collapse selected. Now I will call this folder collision. Okay. And in this one, we have to compute the force that has to be added to each particles in order to solve the collision. And yeah, let's see this. First thing, I would like to normalize this with a mat. And I will use 1 divided by how many particles I have. So 1 divided by the particles. I copy this, and in post add, I'm adding half of it. So Control V divided by 2. And now we have a nice index texture. Okay, now I have here values in between 0, 1, like a very nice ramp, and of course some huge numbers doesn't really affect us. Okay, and what I like to do, it's split top and bottom, and I have to drag here a couple of things. First, the position in the feedback. So select, I will drag. Oh, where's my select? Okay, here I will drag the feedback, and I need another one to drag the radius, so I'll have it here. Now everything we need, we have it. Okay. Now you see our points, we have 12 points, obviously 12 pixels, and 12 by 1 this texture, and this one is 12 by 5. What that means? It means on every column we have the neighbors corresponding with our particle, you see. So first pixel, this particle will have this neighbor indices, okay? And in order to do the math, we have to arrange, to stretch this position and radius texture to match the neighbors, okay? So we can go with a group. Okay, let's group it, and yeah, I also need now let me split again, and I will have this out here. Okay, and now I drag the neighbors like this. And we do this for the radius also. And now we'll we in this texture, what neighbor pop provide us, okay? We don't have the position of the neighbors, we have the indices, okay? And this being black and white, and the texture where we have the positions is in line. That means we can remap with one channel, with a ramp, okay? And we don't need the UV or RG values to remap, okay? Now let's go with remap like this, and we go with UV resolution, and this is RGBA, okay? And yeah, we can see here this pink particle or sphere or point. It has those neighbors in that 2 radius distance, okay? And we'll do the same for the radiuses, okay? And now we have here, it's not a radius, it's the scale only, but if we multiply with such a small radius, we'll see a black texture. So let's go a little bit further with this scale, and then we multiply with the radius, okay? So those are the scales for the neighbors, okay? And what else we need? I will go with the math. Okay, like this, and we go with the floor. And now with a level, we clamp the input 0, 1, and we invert, okay? And yeah, those, we have in this texture here the number of the neighbors. That little thing that we didn't take it as granted for the from the neighbor pop, okay? But yeah, it's very easy to find it, okay? And I would like now to multiply this. First, let me name a little bit. So this would be a mask, okay? This is points. Okay, there's some neighbors. Okay, this is the mask. Here in this group I will name this radius, okay? And for the radi of the neighbors I will call this radi, okay? And now how we solve the collision. I'm obsessed with collision. I have a couple of tutorials already on this particular topic. So we need to sum the radius of the sphere with the radius of the neighbors, okay? So I use this multiply just to clean a little bit the texture, okay? And now, okay. And now let's add them. So we add this, okay? And right now it's good to use a math and scale this down with the radius. So okay, we mask the alpha and let's have nearest pixel. Okay, so I will call this sum of ready. Okay, and again I would like to clean the points, so I use multiply with the points. Okay, and now I want to subtract the points out of the neighbors, so I will do subtract like this. Let's mask the alpha. Okay, okay, and out of this texture here we have the directions to the neighbors. Okay, and we use a math with Pythagoras with length. Okay, and this is the distance. This has to be 32 mono. Okay, now this is distance. Okay, and I want to now I want to go with the distance minus sum of the ready. Okay, because the thing is two different radiuses. Okay, if the sum of them are bigger than the distance, that means we have an overlapping. It's a situation there we have to solve collision. And let's go with subtract like this. Okay, I will mask the alpha, and right after I want to check to see where I have my radiuses bigger than the distance. So I use a math. I go with ceiling. Okay. Okay, and now I go level, and yeah, clamp 0, 1, invert. And what this means, see, where we have white here, only at the bottom. Let's check also the mask. You see that those black pixels above doesn't really count, even though we have white here. So you can clean it by selecting this and yeah, multiply with this. It is not necessary, you know. It will work without that. So let's multiply now like this. Now I want the overlap. It's going back half of the overlapping. So we have the overlap here. We use a math, and we divide it by 2. Okay. Now this we have to multiply this with the normalized vector direction to the neighbors. Okay, and the direction to the neighbors is here. So is this subtract, and now we need to normalize this. Let's build a normalize component. So we chain a null in between, collapse selected, go inside. Inside we need a composite. For this composite we take transform input 1 and divide. And yeah, in order to be more optimized, we can select this distance. We already have it. Okay, so let's go with this. Okay, select this distance. Other way, we use another math, and we compute the length again, but we already have it. Okay, so let's go like this. Now this is the normalized direction from which we take half of the overlap. Okay, so let's multiply like this. Multiply. Now we have here on columns the we have here, you can't see, but on the columns we have the forces, and we have to average them. Okay, in order to average them, we make the average with the points that are in that situation of overlapping, of collision. Okay, and for that, let's use an analyze. I analyze everything with sum on columns. Okay, and then I need to divide this on how many points there are on that column. Okay, so I can go with a select like this. I select the mask, and I use the same analyze like this, and now we go with the composite with divide. Okay, now we divide like this, input 1 and divide. Okay, that should be everything. Okay, let's connect this out. Okay, now let me select everything and make it nearest pixel. Okay, and let's see now. I add those forces. Yeah, we don't need this, and let's see what happened. Oh yeah, everything is perfect. So we solved the collision. Okay, now that the network is almost done, we can go with a much higher amount of particles. Okay, so let's go with 1 to 8, and maybe the radius would be 1 divided by 16. Okay, and yeah, look, super nice. Okay, now maybe you ask how many spheres we can have, and in this version that I have, this one is non-commercial, and you have a limitation for texture, and computing in textures, we are in that limitation. So you can't go in a non-commercial with this technique bigger than 1280. By 1280, it's already a lot of spheres. Okay, so yeah. And I would dare to say this works for 24,000, 32,000 spheres. So, but yeah, I can't check with this inline method. You will tell me if I'm right. Okay. Okay. Let's go just a little bit back with 1 to 8. Okay, now this is nice. I would like to give them colors. Okay, so I use again a noise. This one, let's change the seed to 2 maybe, and this is colored. Again, this is 0.5 here, offset 0.5. Okay, and 32 RGBA. Now a null. I name these colors, make it pink, and let's see the color R, G, and B. Okay, we are good. Okay. And what else I would like to have here, one of my favorite thing to play with is blur. If I use a blur here, you see I have this thing, which is lovely. But the ends are separate, and we can go with repeat, and I reset, and you see the ends are not connected, and this, I believe this is a little bit of error maybe, and since this is experimental, yeah, it's nothing to worry about. So what I found to work in this case is, let's go to sample step and lower this just a little bit, okay? And now, yeah, we have the ends, okay? Now, what I would also like to have here is I would like to have the colors mapped by a circle. Okay, so we have a circle here in the radial. Okay, let's select. So we say radial /out 1. Okay, we have it here, and we map the colors and the radius and the scale. Okay, like this. And yeah, let's go now with something like this, and maybe okay, much more subtle colors. Okay, what we can do now is make this noise moving a little bit. So we go with ABS time dot frame divided by 1024. Okay, and let's have every second sphere being white, or maybe every third, or yeah, you will decide in the end. So okay, now blur doesn't like nearest pixel in here, so okay, this is good. Now let's have that white thing. So let's go with a constant, and this constant is 1 by 1 pixel, 32 mono, and now I group this. Can group with 3 or with 2. Let's go with 2, but 0. Okay. And now we have first pixel white, second one black, and we want to continue this, and we'll go with a group in which we drag this particle. But let's set first this to pixel, and now we have something we can screen above the colors. Okay, and we have this. So, and yeah, this is pretty nice. And now I will show you what it's this noise. You see, they start in a plane, and the collision, if the z is 0, the blue is 0, yeah, the collision is solved in one plane. This is the reason here we went with just a little bit of noise, okay? Just a little bit, yeah. And we can increase, let's go bigger with this, and maybe smaller, way smaller radius, I would say. Okay, and now we can play with the blur. So yeah, something like that. Now we can go with a much smoother sphere if we want that. What I like to show you is what if we don't blur the entire texture. Okay, the entire texture is 1280. Okay, let's see something that I didn't find in this experimental version, and I found out that it's gone from the newer official version, is point repack. Now I do love point repack. Point repack, let's repack this texture with I will drag the resolution, and here I go with 8, right? And we go divide by 8. Okay. Now let's like this. Okay. And now I have 8 rows. If I go into the blur with this, I will ruin everything, because in my feedback loop I have just inline texture. So I need another repack right after the blur. Okay, and I go with 1280 by 1, and yeah, let's go now like this. And just a second, this blur here goes only for, so it's 0 here. Okay. And let's go with hold, and now we have yeah, couple of snakes. Okay, and you can have plenty more if you go here with 64, and let's go 64 here also. Okay, and yeah, you see they are short now, and obviously you control everything with the blur. So yeah, I believe this is it. Everything I wanted to show you, and I really hope you like this method, and yeah, thank you so much for watching. I will have a lot of tutorials using this neighbor pop, as yeah, it's my favorite. So thank you so much for watching this. As I said, it will be available for my patrons in tier 2 play, and I also have some advanced one for tier 3 learn. And yeah, thank you massive for your support, and I'll see you in the next one. Bye.